Good afternoon, everyone. My name is Anthony Roblick. I'm with the Municipal Stormwater Engineering Unit. Welcome to Module 2 of the Stormwater Management Design Review course. And it's 6 after. It looks like we have most of the folks who registered in here. So we'll go ahead and get started now. Just as a reminder to everyone that we are recording this module, as with all the modules in this course. So we ask that you please keep your microphones muted during the presentation. And if you have any questions, to please type them into the chat and our staff will respond. All right, so with that, this is the agenda for Module 2 today. We'll begin the day with a presentation on stormwater calculations, and that'll be presented by myself. Then we'll move on to soil testing, which will be presented by Lisa Schaefer. And that's going to be followed by a presentation from Dr. Dick McGee from NJCAT on MTDs. And after those three presentations, we'll have a quiz 2, and we'll end the day with the quiz review. And as Lisa mentioned already, the schedule usually runs a little tight for this module. So time permitting, we'll take a quick break maybe in between some of the presentations. All right, so let's get started with this first presentation here, which will cover stormwater runoff calcs. So this material is included in the course because the DEP has found from some of the previously conducted MS4 audits that the stormwater calculations are oftentimes not performed correctly. So while most of you are probably familiar with these methods, as evidenced by some incorrect calculations in our reviews, we're including this just as a brief review in the course. And later presentations in Module 3 we'll highlight some of these errors in a little more detail, and we'll also have some example projects in Module 4 next week. Okay, so the 6 major goals of this presentation are here. And the first one is understanding the Natural Resources Conservation Service, or NRCS methodology, and that's formally referred to as TR55, and it's used to calculate peak flow rates, volume of runoff, and produce hydrographs as well. Then our second objective is using the NRCS methodology to actually calculate runoff volume. Then we'll move on to the third goal, which is to calculate the time of concentration. And we'll cover some of the examples in our version of Chapter 5 in the B&P manual. Next, we'll take a more detailed look at hydrographs and rainfall distributions. Then we'll move on to the NJDEP two-step method for calculating runoff from an unconnected impervious area. And our last goal we'll cover when exfiltration may or may not be used in the stormwater routings. So first we'll take a closer look at the NRCS methodology. So the requirement is found in the rules at the location that's noted at the top of the slide here, NJAC 7:8-5.7A1. And so this method is listed here in the rules. It's the USDA Natural Resources Conservation Service, or NRCS methodology. And like I mentioned before, it was additionally described in TR55. However, TR55 has been superseded by the National Engineering Handbook, or NEH Part 630 Hydrology, and a link to that is at the bottom of the slide here. The NRCS method can provide total stormwater runoff volume, the peak flow rate, and produce hydrographs. Under the NRCS method, different synthetic rainfall distributions and unit hydrographs can be applied to produce the stormwater runoff hydrographs in accordance with geographical differences that may affect the rainfall pattern of each storm event and the runoff pattern in a region. And that's dependent upon factors like ground slope and ground condition. There are plenty of software packages that use this methodology, and in later presentations, we'll cover what to check in your reviews with those. The NRCS method can be used for a drainage area of any size, but the area is subject to the rule requirement that the relative stormwater runoff rates and volumes of pervious and impervious surfaces be separately considered to accurately compute the rates of and volume of stormwater runoff from the drainage area. So the NRCS runoff equation was developed to estimate total stormwater runoff from total storm rainfall. And the soil and cover conditions determine a parameter called the curve number, or CN, which we will discuss shortly. But first, we'll take a look at the equation that uses this parameter. So we can calculate runoff depth, which is Q here in inches, by using the NRCS equation. P here is our rainfall data for a particular design storm. The next parameter is the initial abstraction, or I sub A, which is the stormwater volume loss before runoff begins. And that includes the water retained in surface depressions, water intercepted by vegetation, evaporation, and infiltration. And for New Jersey, initial abstraction is equal to 2/10 of the potential maximum retention, which is S. And for that, we need the curve number to calculate. So after determining the curve number and calculating S, we would be able to calculate the total depth of runoff. So that'll bring us to a little discussion on curve numbers here. And curve number is abbreviated CN. It's an empirical parameter used for predicting direct runoff or infiltration from rainfall excess. CN is a function of the hydrologic soil group, or HSG, and land cover, and that's such as woods, pasture, or impervious cover. HSGA is the most permeable group and produces the least amount of runoff when thoroughly saturated. The designations go alphabetically from B to D, with D being the least permeable group and having the highest runoff potential. The preliminary soil group classification can be found on the NRCS Web Soil Survey, but further investigations may be necessary, and Lisa will cover that in the next soil testing presentation. And she'll also go over the default HSG values that we may assume. So once you have determined your HSG or are using the default assumptions that are allowed, you can determine the curve number value to input. So shown here on the right is table 9-5 from the National Engineering Handbook. There are many different land uses listed here. A common land use you'll see is denoted by the arrow towards the top of the slide, which is for good condition open space. Notice the CN values increase as the soil group goes from HSG-A to D. So there's going to be more runoff for a D soil than for an A soil, and that's for a given land cover. It's crucial to use the CN value that best identifies the ground cover type and hydrologic condition. If the analysis uses pre-development CNs that are lower in value, the analysis is considered conservative. But if the analysis uses pre-development CNs that are too high, the analysis is considered incorrect. Note the requirement from the stormwater rules that's shown in the yellow box at the upper left of the slide, and that's regarding which CN value to use. And this requirement also appears in the local SCOs. Remember that for an impervious surface, the curve number is always 98. And lastly, note the cautionary info in the white box at the bottom left of the slide. And that means that the values in the red box that's shown on table 9.5 here are not what you will typically see in your calculations for a development project. All right, so what do we do if there's more than one curve number? Due to the nonlinearity of the equations and losses from initial abstraction, it's important, and it's also required in the rules, to compute separately the runoff volumes from pervious and impervious areas instead of averaging the curve numbers. Particularly for smaller, more frequent storms, averaging is going to underestimate the volume of runoff generated by the impervious surface on a site that has pervious land cover as well. And using composite CN values is one of the common errors that we found in our reviews. So for example here, if we analyze a site with 1 acre of impervious with a CN of 98 and 2 acres of grass lawn with a CN of 65 for the water quality design storm, using a composite CN for the site would result in roughly 70% less runoff volume than if volumes were calculated separately for pervious and impervious areas. So using a composite CN means the BMP is likely undersized for the smaller storms, including the water quality design storm. And when that happens, the BMP won't merit the pre-approved rating for total suspended solids removal. All right, so here's another example, and this one's from Chapter 5 of our BMP manual. Just a note before I read this example here, this example mentions the 2-year design storm, and it doesn't really make a distinction between the current or projected 2-year storm event, and that's because it's not necessary to do for the purpose of this example, which is just to show that for a given rainfall depth and slope, how different calculated runoff volumes can be from the different considerations. All right, so from this example, we see that the runoff from the impervious surface will flow directly into the grass swale. And so this is going to be a directly connected impervious surface. And when looking up the CN for grass from table 9.5, we get a CN value of 39 for HSGA soils. And the CN for impervious cover, of course, is always 98. So next we'll calculate the volumes produced for this storm using a correct method, which is separating the pervious and impervious runoff volumes. And then we'll compare that to the incorrect averaging method. So using the NRCS runoff equation, we calculate S using our CN values and input the rainfall data to calculate the depth of runoff, which we then multiply by the area on which it falls to compute the volumes. And we do this for both the pervious and the impervious areas. So for this example, the green box here shows the computation with the CN separated out, where the yellow box uses a composite CN. So if we take a look at the yellow shaded box, we can see that averaging the CNs in this example yields a volume that is only 37% of the total volume we calculated when following the rule requirement to compute runoff separately. So calculating the runoff from pervious and impervious surfaces separately yields a total runoff volume of 1373.3 cubic feet. And while using the incorrect composite CN value for both surfaces only yields 508 cubic feet of total runoff. So this is a simple example, but it does a decent job of illustrating how different the results can be and why we always use the method that's identified in the green box. So moving on to the next goal, which will cover time of concentration. Previously, we saw the definition from the rules that it is the time required for stormwater runoff to travel from the most hydraulically distant point on a site to a point of analysis, T sub C. And it's an important parameter to get right in the calcs. So we'll go ahead and take a look at the next graphic here to understand why. So any site consists of one or more drainage areas. And a drainage area is a land area where all stormwater runoff produced by that area converges to a single point. Drainage areas are sometimes also called drainage basins, which are determined by the topography. They can range in size from very small up to tens of thousands of square miles. And by looking at this watershed, you'll see that due to the slopes of the area, any drop of water that falls in the valley between those two yellow shaded areas will eventually make its way to the river. And any drop of water that falls on the other side of the ridgeline will flow somewhere else. Those areas are part of a different drainage area. So something important to note is that the most hydraulically distant point doesn't necessarily mean the furthest point in distance. In this image, the surrounding terrain on each side up to the ridge lines are part of the drainage area directing runoff to the point of analysis that's marked by the red dot at the bottom. So even though runoff has to move maybe much further to get from the mountains to the outlet of the river, the most hydraulically distant point may be somewhere else, somewhere in the forested area. So in Module 1, we presented how various land uses, slopes, and other factors all affect how fast stormwater actually moves across the land. For example, dense vegetation like forest causes the runoff to move more slowly than smoother land surfaces, and steeper slopes cause runoff to move faster. To compute the time of concentration, surface runoff, channel shape, and slope are the three parameters that must be characterized for each segment of flow along the flow path. Additionally, the energy level of the flow also factors into the calculation, and there are three categories to classify the type of energy a flow may exhibit, and those are the three listed here: sheet flow, shallow concentrated flow, and channel flow. The two most likely to occur in site calculations are usually sheet flow and shallow concentrated flow. So sheet flow is usually at the headwaters and over plain surfaces. This is where runoff forms a thin sheet that is low in energy, also low in velocity and depth. This is what we may see on lawns or in parking lots. In Chapter 5 of our BMP manual, we note that sheet flow does not occur after 100 feet, and there's more to cover on that in a couple of slides. So the second one here, shallow concentrated flow, occurs where runoff begins to coalesce and pick up some velocity. The depth is greater than 1/10 of a foot, but doesn't really exhibit a defined channel. And lastly here, we have channel flow. That can be seen in aerial photographs and on GIS and USGS maps. It's essentially flow in some type of bounded channel, which is higher in energy state and relatively faster than the other two types of flow. All right, so now that we covered the types of flow energy, we can discuss the velocity method. So from the National Engineering Handbook, the velocity method can be used for a project site or drainage area to calculate time of concentration. And remember that the time of concentration is the sum of all the travel times for each type of flow in a segment, and that's along the most hydraulically distant flow path. So you can have more than one occurrence of sheet flow, for example, because one of the defining parameters, such as slope, has changed. This requires a calculation for each type of instance of flow over the segment or path in which it occurs, and then just summing them up. Just a note, going forward, the assumed minimum value of 6 minutes, which was previously published in Chapter 5, must now be replaced by a correct calculation. So therefore, it's important to check the reported values in your reviews. If the T sub C is calculated incorrectly, it could potentially impact the neighboring land, the infrastructure, or even a local waterway. Okay, so Chapter 5 of our BMP manual also changes the potential maximum sheet flow length in accordance with the National Engineering Handbook Chapter 15. So for the pre-construction condition, we assume that sheet flow occurs for up to a maximum of 100 feet, unless there is something physically in contact with the flow of stormwater runoff, such as a swale or a curb or inlet, and that'll prevent the sheet flow from occurring. And that's regardless of whether the surface is impervious or pervious. And so that's to say if the site conditions only create, say, 75 feet of sheet flow, then we use 75. But the max value allowed is 100 feet. And for the post-construction condition, the maximum sheet flow length should not exceed either the McEwen-Speece limitation or 100 feet, whichever is shorter. And the equation to calculate the McEwen-Speece limitation is noted under the second bullet here. And that's where L is the sheet flow length determined by the McEwen-Speece limitation. S is going to be the slope, and N is the Manning's roughness coefficient. So if the sheet flow length calculated by McEwen-Speece limitation is less than 100 feet, then we would use the length determined by that calculation. If the sheet flow length determined by McEwen-Speece exceeds 100 feet, then the sheet flow length must be limited to 100 feet because that's our max. But keep in mind, this criteria is for the maximum sheet flow length that can be used. So again, if site conditions have a physical obstruction at a distance that's less than both the McEwen-Spiess calculation or the 100 feet, then that shorter distance is the one that should be used. Okay, so now that we covered the sheet flow length limitations, we can talk a little bit about how travel time for sheet flow is calculated. So this is the travel time equation for sheet flow, and that's using the Manning's kinematic equation, and listed here are the parameters which must be identified. So those parameters are the sheet flow length, which we just talked about, the Manning's roughness coefficient, the current and projected 2-year storm event rainfall depth, and that's depending on which storm event calculation this travel time is serving as input to. And lastly, the slope of the hydraulic grade line. Okay, so the next couple of slides will go into a little more detail on the roughness coefficient and the 2-year rainfall depth parameters. So first, let's look at the roughness coefficient, which is also called the Manning's N value. This table here is found in Chapter 15 of the National Engineering Handbook. And the roughness coefficient is a measure of the roughness of a surface or a measure of a surface's resistance to flow. And there are different tables for each energy state of flow. So the roughness coefficients for sheet flow are organized from smooth to rough. So if, for example, a site has dense grasses, we would use a Manning's N value of 0.24. And that's for calculating the travel time for sheet flow. So note that the lower the N value, the quicker the runoff will travel. For example, impervious surfaces here have a roughness coefficient of 0.011. Also important is that the New Jersey BMP manual states that the maximum roughness coefficient for sheet flow in New Jersey is 0.4, and that corresponds to woods with light underbrush. So we wouldn't use a roughness coefficient in New Jersey that is greater than 0.4. All right, next let's discuss the 2-year 24-hour rainfall depth parameter. So if you recall, I briefly mentioned a couple of slides ago that we use either the current or projected 2-year storm event rainfall depth for this parameter. And that's dependent upon which storm event the sheet flow travel time is being calculated for. So when calculating the travel time for current storm events, we use the precipitation depth for the current 2-year storm, which Peter noted in Module 1 is calculated by multiplying either the NOAA precipitation frequency data server rainfall depth or the county rainfall data for the 2-year storm by the current precipitation adjustment factor. And when calculating the travel time for the projected storm event, we use either the precipitation depth for the projected 2-year storm from the NOAA data or the county rainfall data, and we multiply that by the precipitation change factor for the 2-year storm. So the P2 parameter will vary depending on whether you're calculating the sheet flow travel time for either a current or a projected storm event. So on the slide here, you could see a screenshot from the NOAA precipitation frequency data server. This one happens to be for Trenton. So after navigating to the NOAA website, we got here by selecting New Jersey, and then precipitation depth and partial duration for the time series type. You will end up with a chart like this one here, but it'll extend a little further in duration and storm recurrence interval. Here you can find the column for the 2-year storm event and then the row for the 24-hour duration. And the rainfall depth is listed here in inches. So from this chart, the 2-year 24-hour rainfall depth is going to be 3.33 inches, and that's circled in red. And you can alternatively use the county data introduced in Module 1 for this storm. But after that, that's not all. After that, we have to multiply this rainfall depth by either the current precipitation adjustment factor or the future precipitation change factor for the 2-year design storm. And that's depending on whether this sheet flow is calculated for a current or projected storm event. And so since the site we're looking at in this example is in Trenton, we would look up the current precipitation adjustment factor and future precipitation change factor for Mercer County, and which happens to be 1.01 and 1.16 respectively. And then we use that to multiply by the 3.33 inches that we got from NOAA, and that will result in a P2 of 3.36 inches for the current storm events and 3.86 inches for projected storm events. Okay, so that's how we calculate P2 for a site that is located within a single county, and that's most sites. But how do we calculate P2 if a site lies on a county line and portions of the site are located in two separate counties? And in that case, to calculate P2, we would first have to adjust each county's 2-year storm precipitation depth by either the county's respective current precipitation adjustment factor or future precipitation change factor, whichever is appropriate, and then perform the area weighted average. So as an example, if we are looking to calculate a sheet flow travel time to ultimately serve as input for modeling runoff from a current storm event, and we have a site where 1/3 of the site is located in Middlesex County and 2/3 is located in Mercer County, the first thing we should do is calculate the P2 variable, or to calculate the P2 variable is to obtain the 2-year rainfall depths for each of the counties from either NOAA or the county rainfall data. So in our case, we use the county rainfall data. And these two values may be the same if you were pinpointing the site on the NOAA website, but in our case, for the 2-year storm event, that's going to end up being 3.35 inches for Middlesex County and 3.31 inches for Mercer County. So then we multiply those rainfall depths by each of the respective 2-year current precipitation adjustment factors, since we're ultimately looking to model a current storm event. And again, if we were looking to model a projected storm event, we would multiply those rainfall depths by each of the county's 2-year future precipitation change factors instead. But the current precipitation adjustment factor for the 2-year design storm is 1.00 for Middlesex County and 1.01 for Mercer County. So then our final step is going to be to perform the area weighted average. So since 1/3 of our site is located in Middlesex County, we would multiply that adjusted rainfall depth by 1/3. And we would do something similar for the Mercer County adjusted rainfall depth, multiplying that value by 2/3. And then summing those values together, this results in a final P2 value for current storm events of 3.35 inches. Okay, next we'll cover how the travel time for shallow concentrated flow is calculated. So this travel time is equal to length for a particular segment divided by the estimated velocity, and that's multiplied by 3,600 for the conversion from seconds to hours. And velocity is estimated based on a site's surface condition and slope. So the value for the flow velocity can be determined from figure 15-4 of part 630 in the NEH. The velocities plotted are average values and are a function of watercourse slope and the cover condition of the channel. So this source was derived from solving Manning's equation for a wider variety of different land covers. The y-axis here is our slope in feet per feet, and the x-axis is the average velocity in feet per second. So you would draw a horizontal line from your slope on the y-axis over to the condition line, and then draw a vertical line down to the x-axis to find where your value for velocity is. You may still see citations for a TR55 source, which is a simplified source, but remember that that has been superseded, so make sure the graphical source used is the one shown here from the NEH. So the last travel time we need to calculate is for open channel flow. For this calculation, we need the length of this segment, the roughness coefficient for open channel flow, which is different from the other Manning's N value that we previously covered. the hydraulic radius, and the channel slope. And Manning's N values for open channel flow can be obtained typically from like standard hydraulics textbooks. We don't have anything published in our B&P manual on that. The hydraulic radius is equal to the cross-sectional flow area divided by the wetted perimeter. And the wetted perimeter is the surface of the channel bottom and the sides that are in direct contact with the flow. Don't use this equation if you have flow under pressure in a pipe. That uses a different equation. And you shouldn't see this type of flow that often in stormwater calcs for development. Okay, so let's work through an example for calculating the time of concentration. So this states that for a site located in Mercer County, stormwater runoff flows through a wooded drainage area along a flow path measuring 1,000 feet in length. And it's consisting of sheet flow over an area with a 0.5% slope, and then shallow concentrated flow over an area with a 1% slope. It's asking us to calculate the time of concentration using current rainfall data. So a slope of 0.5% is equal to 0.005 feet per foot, and that's for woods. The Manning's roughness for sheet flow in New Jersey is 0.4. So the sheet flow length is calculated by using the formula from the McEwen-Speece limitation criterion, and that comes out to 17.68 feet. And since this example is asking us to use the current rainfall data, as we previously saw, applying the 2-year design storm current precipitation adjustment factor to the 2-year 24-hour rainfall depth from the NOAA website results in a P2 of 3.36 inches. But for sheet flow length, and this wasn't mentioned in the example statement, but in this case, there's actually a physical obstruction on this site that limits sheet flow length to just 15 feet. So we're not going to use the larger distance of 17.68 feet calculated by McEwen-Speece, and instead use the smaller distance of 15 feet, which represents the actual site conditions. So plugging all this into the equation yields a travel time of 8 minutes. So now we'll calculate the shallow concentrated flow travel time. And remember that the total flow path is 1,000 feet. So since the sheet flow segment length was determined to be 15 feet, the length of the shallow concentrated flow segment must be the remaining 985 feet. So the value for the flow velocity can be determined from the figure 15-4, which we mentioned earlier. And for this example, a horizontal line is projected across from the y-axis at the tick mark denoting the 1% slope to the curve representing forested areas. And the corresponding velocity on the x-axis is going to be 0.25 feet per second. And this value is then entered into the equation for travel time, and we get 65.5 minutes. And so our answer is going to be the sum of the travel times for both the sheet flow and shallow concentrated flow, and that results in a final answer of 73.5 minutes. Okay, next we'll discuss developing hydrographs, which we defined earlier as the graphs depicting the flow rate of runoff versus the time passed at a specific point of analysis. A hydrograph can provide a lot of information about stormwater runoff, including the time of concentration, the time at which peak flow occurs, the peak flow rate, and the volume of runoff generated. So first, we should talk about the unitless synthetic hydrographs for the NRCS methodology. So unit hydrograph is a direct runoff hydrograph resulting from 1 inch of excess rainfall. The unit hydrograph influences the shape of the runoff hydrograph, particularly the peak rate of discharge. Given a watershed's unit hydrograph, we can calculate the theoretical hydrograph for any storm event. In an ideal world, a unit hydrograph would be developed by metering the flow from a watershed, but since this isn't a very practical solution, we use synthetic hydrographs instead. In general, we use 2 synthetic hydrographs, which are the Soil Conservation Service, or SCS, dimensionless unit hydrograph, and the Delmarva dimensionless unit hydrograph. And most software packages have settings that allow selection of either of those. So first, let's talk about the SCS, which is based on an average of natural watersheds with various sizes and geographic locations, which allow us to predict how an unmetered watershed will react to rainfall. So it's important to note that within the state of New Jersey, the SCS unit hydrograph is used outside of the coastal plain, except in very rare circumstances. So shown here with an orange curve is the SCS unit hydrograph. The corresponding rainfall event is shaded in blue. As you can see, the timing of the hydrograph is based on the time of concentration from the drainage area, which is highlighted in yellow. There is some runoff at the start of the event, and more runoff as areas further up gradient of the point of analysis begin to contribute. And the most hydraulically distant point eventually stops contributing, and the runoff continues to taper off. And the volume of runoff produced by the site in response to the rain event is equal to the area under this hydrograph. So in development of this runoff hydrograph, the runoff discharge is nonlinear in relation to the time of the rain event in accordance with the NRCS observations from many natural unit hydrographs developed from various watersheds. The dimensionless unit hydrograph that was developed has a peak rate factor or shape factor of 484, which means that 48.4% of the total runoff volume is discharged before the peak time, and the remaining 51.6% of the total runoff volume is discharged after the peak time. The peak rate of runoff is the maximum height of the hydrograph. And you can usually see the shape factor on the printouts provided in the stormwater management reports. So that's something to check in the reviews. And again, for this particular hydrograph, it's usually around 484. So the second commonly used dimensionless unit hydrograph is the Delmarva unit hydrograph. The Delmarva hydrograph is suited for the flat coastal areas in Delaware, Maryland, Virginia, which is where it got its name. And it's also for similar areas in New Jersey. So shown here is a comparison of the SCS and Delmarva unit hydrographs. When calculating the peak flow rate using the Delmarva hydrograph, we use a shape factor that is lower than the SCS unit hydrograph. The Delmarva shape factor is something closer to 284 or 285, and that's depending on the software used. The Delmarva unit hydrograph will not affect the determination of runoff volume, but will result in lower peak discharges when compared to the SCS unit hydrograph. The lower shape factor for the Delmarva means there's less volume under the rising limb, so the hydrograph is a bit shorter in height, but it is also longer in duration. So this comes in part from the gentler slopes of the terrain and the lower level of urbanization in those areas. So the Delmarva hydrograph must be used in calculating pre-construction and post-construction peak flow rates for the current and projected 210 and 100-year design storms in the coastal plain region of New Jersey, except in specific circumstances, which we'll cover in a couple of slides. Also note that if the Delmarva is used in the pre-condition, it must also be used in the post-condition. That's likewise for the SCS. Projects which lie on or near the boundary where the Piedmont and coastal plain regions of the state should be modeled with both the standard and Delmarva unit hydrographs and results compared with actual field conditions to determine which unit hydrograph offers the best fit. So where's that boundary exactly? This is just a zoomed in view with a few points of interest added to the same map from the previous slide. The blue line dividing the state is the boundary of the coastal plain, and the hyperlink here is to the Bureau of Geologic Information Systems for physiographic province metadata, if you're interested. You'll want to be careful in outlying parts of locations near the border of the coastal plain, for example, parts of Princeton and Monmouth Junctions, and a little bit northwest of Trenton. The municipal stormwater management plan, where the site is located, may include this information as well. However, this is possibly your best bet in determining whether a site is in the Piedmont or coastal plain region of the state, and it's using the application shown here. So this is a GIS layer noting the different physiographic provinces within the state, and this is from the NJDEP Bureau of GIS website. So this allows the user to look up the actual site address to very easily make a determination as to which physiographic province a site falls in. And the link noted here on the bottom of the slide will direct you to this GIS application. So when not to use the Delmarva dimensionless unit hydrograph. So the Delmarva must not be used outside of the coastal plain of New Jersey. For another instance, use of the Delmarva unit hydrograph is not allowed when sizing manufactured treatment devices or MTDs because it may underestimate the peak flow rates. And lastly, when a site is within the coastal plain and the design engineer can prove to the satisfaction of the review engineer that the conditions for applicability of the Delmarva are in no way present anywhere in the watershed. For example, if the site is completely paved or there are very steep slopes present, say greater than 10%, then it may be more appropriate to use the SCS hydrograph. In addition to the rainfall depth data, we have to know how rain falls during a storm event if we're going to create models and design BMPs to address runoff. So to estimate a rainfall event for design and planning purposes, between 1961 and 1977, NRCS developed synthetic rainfall distributions from historical records for the different regions of the country. The basic shape of the distributions all assume rain starts gently, increases in intensity towards the middle portion of the storm event, and then tapers off. The type 3 distribution was previously used for about 20 years. Now we require use of the NOAA C and D distributions, depending on which county we're in, per the 2012 bulletin from NRCS. A coworker here has done some modeling using these new synthetic rainfall distributions, and we've learned that you can expect on average to see higher peak flow rates when using the C and D rainfall distributions as compared to the old type 3. So here's a map of the Northeast US depicting the regions. In the bottom left, you can see an image that shows a zoom in of New Jersey. So this figure is from Chapter 4 of the NEH and is also included in Chapter 5 of our BMP manual. And you can see the red shaded areas will use the NOAA C distribution, while the yellow shaded areas will use the NOAA D distribution. And you should be able to download text data using this hyperlink here. And we've also added a link to make this information available as an Excel file from the DEP webpage. And those are for the NOAA C and D distributions. Okay, so now we'll have another quick example. So this example is asking us to apply the current precipitation adjustment factors to the rainfall data for a site located at Trenton Station 2 using the NOAA website. So unlike the last example when we were calculating time of concentration and looking up or looking to apply the factors to just a 2-year storm event, now we are looking for the current rainfall depth for the 210 and 100-year design storms. So the first thing we do is the same as in the last example, is we would navigate to the NOAA Precipitation Frequency Data Server website, and the URL here is provided under step A there. And then we would select New Jersey from the map. From there, we would make sure that the data type selected is precipitation depth. And again, the time series type selected is partial duration. That's shown on the left side there. And I think the website defaults to those selections, but just check to make sure. Next in step B on the right side is under the select location by station option. We would select the Trenton 2 station from the drop-down list. And then in the next step, we would scroll down the web page to the point precipitation frequency estimation selection. making sure that the tabular data tab is selected. The rainfall depths we are looking for will be found in the 2, 10, and 100-year storm recurrence interval columns in the row labeled 24-hour for the 24-hour storm duration. And those values are outlined here in red under step C. And then the last step, we will apply the current precipitation adjustment factors to the rainfall depth values that were retrieved from the NOAA website. And the current precipitation adjustment factors can be found in table 5-5 of the stormwater management rules. And in this case, we would look at the row for Mercer County, since the site is located in Trenton. And so those adjustment factors would be 1.01, 1.02, and 1.04 for the 2, 10, and 100-year design storms, respectively. And when applying those factors to the NOAA data, we get 3.36, 5.09, and 8.48 inches for each of those design storms. And if you aren't familiar with using the NOAA precipitation data frequency server, there are more details to be found in Chapter 5 of our BMP manual. Okay, next objective. So an important approach to managing stormwater runoff is the incorporation of new impervious cover that is not directly connected to a site's drainage area or drainage system. And this is now extra important with the green infrastructure rule requirements of the stormwater rule. So to slow down runoff generated by impervious surfaces, certain key aspects must be addressed. Runoff from unconnected impervious areas must undergo sheet flow onto adjacent pervious areas, where a portion of the impervious area runoff is given an opportunity to infiltrate into the soil without causing erosion and further sediment transport to whatever is down gradient. Under certain conditions, this technique can help in providing both groundwater recharge and stormwater quality treatment for small rainfall events, as well as reduce the overall runoff volume that must be treated or controlled by down gradient BMP. So there are 5 conditions that must be met for an impervious area to be considered as an unconnected impervious surface. Here are the first 2 conditions, and these basically say that the runoff must enter the pervious area as sheet flow, and it must remain that way. And the other 3 conditions ensure stability and maintain the sheet flow. For this reason, there's a limit on the steepness of the slope to 8% for the down gradient pervious area. And there are 3 additional requirements applicable to either of the 2 calculation methods. Important to note here is that the minimum sheet flow length across the down gradient pervious surface must be 25 feet. Okay, so there are 2 calculation methods, as I just mentioned. The first is the NRCS composite CN with unconnected impervious, and that's from Chapter 9 of the National Engineering Handbook. And that one has a 30% limitation on the impervious area to the relative to the combination of impervious surface and receiving pervious surfaces. And the second method is going to be the NJDEP 2-step method, and that's the one that we're going to take a look at right now. So as an example of the 2-step method, we've got sheet flow over an impervious surface of 25 feet, which doesn't exceed the maximum allowed flow path length. And we have 75 feet of sheet flow over the down gradient impervious area, and that meets the minimum requirement of 25 feet. So we use the NRCS runoff equation from earlier to compute the volume generated by the impervious area, and that comes out to 1362.5 cubic feet. And the next step is to assume that this runoff is evenly distributed as rain falling on the adjacent pervious surface. So to begin that step, we take the runoff volume produced by the design storm falling on the impervious area, and in this case, it's going to be the current 2-year storm event. And we divide that previously calculated volume by the area of the down gradient pervious surface to get rainfall depth, and we convert the units as necessary. We then take that rainfall depth and add it to the current 2-year storm rainfall depth, which also falls on the pervious surface, to get a total effective rainfall depth. And in this case, it's 4.59 inches. And now we can use the NRCS equation for the pervious area, inputting this total effective rainfall and the appropriate on-site retention S to get the effective depth of rain falling on the pervious area. And we can then convert that effective depth to effective volume by multiplying by the pervious area, and that results in 156 cubic feet, which is a good amount of reduction in volume. Okay, so now we can move on to our final objective for this presentation, and we'll briefly go over some of the other updates to our BMP Manual Chapter 5. There's, as with the rest of this presentation, there is quite a bit of material on these next slides, so you'll definitely want to go and read through Chapter 5 on your own, because this is just going to be a brief overview. So here are the first requirements for using exfiltration in routing calculations, as listed in Chapter 5 of our BMP manual. So exfiltration is only allowed for certain small-scale green infrastructure BMPs that infiltrate runoff. All soil testing must follow Chapter 12 requirements, which will be further discussed by Lisa in the next presentation. Also, all design criteria as provided in the respective chapter of the BMP manual must be followed before the BMP can be approved, and pre-treatment must be included. That's unless otherwise so stated in the BMP manual. And an exception to pre-treatment would be for those really small-scale BMPs where the drainage areas are less than or equal to an acre. So now we'll talk a little bit about the pre-treatment requirement, because that extends beyond just being a requirement for exfiltration. So each of the subchapters in Chapter 9 of the BMP manual were revised. Chapter 9 is now the BMPs that are small in scale and also meet the definition of green infrastructure, because they allow stormwater to be treated either through vegetation or soil, provide for reuse, or infiltrate runoff into the soil. There are BMPs in Chapter 10, which are also green infrastructure, but are larger in scale and only used to meet the stormwater runoff quantity requirement. And their use and limitations are detailed in the summary on their respective BMP manual chapters. And they're also listed, these are the large-scale GI BMPs. They're also listed in Table 5.2 in the Stormwater Management Rules. And then lastly, Chapter 11 BMPs are not considered green infrastructure. So accordingly, pre-treatment is an important design criteria. If you do not see pre-treatment listed under the basic design criteria for a particular BMP in our BMP manual, it's under the type-specific design criteria. Roof runoff can be treated by certain measures that are shown here on this page, and there's more details on these particular measures in Chapter 9.1. So the requirement for pre-treatment of roof runoff can be waived under the conditions listed here. For example, if a building that is significantly taller than any of the surrounding trees and doesn't have a vegetative roof should not need the pre-treatment. However, when making that determination, the review agency should consider or must consider the mature height of any surrounding trees. When using another BMP for pre-treatment, it must be designed in accordance with the design requirements outlined in its respective chapter. Always check the BMP manual for the specifics. Roof runoff that is commingled with surface generated runoff must be treated per the manual. For subsurface infiltration basins, pre-treatment may consist of any of the BMPs found in the manual, and 80% TSS removal by the pre-treatment is required. And another note here is small-scale bioretention systems designed to infiltrate that have flow entering as sheet or overland flow may alternatively use a 5-foot wide gravel or stone strip to filter runoff instead of other forms of pretreatment. All right, so back to the requirements for using exfiltration. So where can't you use exfiltration? Exfiltration cannot be used with any under-drained BMPs because exfiltration is removing runoff volume from the system, and under-drained BMPs don't really allow for that. Also, for those sites in special areas or that have no runoff leaving the site in the pre-construction condition, exfiltration can be used for an entire storm under those conditions. You must determine which is the maximum storm for which no runoff leaves the site in the existing condition, or if infiltration of the entire storm is required by law or rule established by either the Pinelands Commission, the Highlands Council, or other stormwater review agency that has jurisdiction over the project area. Okay, next, groundwater mounding analyses are required when using exfiltration in the routings. These are the conditions that also apply. Basically, the soils must be tested in accordance with Chapter 12 of our BMP manual, and you must also follow Chapter 13, which is specifically about the groundwater mounding analysis method to be used. Okay, here are some additional things you need to know about groundwater mounding. The groundwater mounding analysis has determined that an adverse impact will occur if the resulting groundwater mound reaches the bottom of the BMP, or if the temporary localized increase in the water table encroaches upon a building or other subsurface structure, including septic systems. When an adverse impact is the result, further modification to the size of the infiltration area of the BMP or reductions in the exfiltration rate must be performed until the adverse impacts are eliminated. A groundwater mound that reaches the bottom of the BMP means that the hydraulic gradient is reduced, which is another way of saying that the BMP cannot infiltrate runoff as fast as originally expected. So you will have to redo the routing calculations to calculate new peak flow rates if that happens. We're not going to run through it here, but you can refer to Chapter 5 of the BMP manual for the methodology to be used, specifically examples 5-6 and 5-7. And then also groundwater mounding is itself a presentation in Module 3 next week. So we'll take a much deeper look at it then. Okay, so that concludes this presentation. Thank you for your attention. Here's my contact information should you have any questions. You could also reach out to our Bureau email account that I think Lisa posted in the chat if you scroll back up to the top. I'll turn this over now to Lisa for the soil testing presentation, unless we have time for a quick break.
Yeah, yes, well, I think we will take a 10 minutes break and please come back at 2:14. Thank you.
Hello, everyone. It's 2:14, so welcome back from your break. I hope that you're enjoying the training so far. My name is Lisa Schaefer, and I'm another one of the engineers in the Municipal Stormwater Engineering Unit. So today I will be presenting the soil testing requirements. And 7 months ago, we updated Chapter 12. So when you are doing your reviews, please be sure to use the latest version. So understanding the character and saturated hydraulic conductivity of surface and subsurface soils at a proposed land development site is crucial to the design of stormwater BMPs that meet the requirements of the stormwater management rules. So I'll be going over the requirements, what's to be submitted, and what should be in the stormwater management report for a major development project. So before I go further, I also want to mention that as part of our audit experience, soil testing has been one of those areas that we often found to not have been done correctly. All right, so this presentation will cover the information from Chapter 12, and that includes the reasons why we need soil testing to determine hydrologic soil group, or HSG, the soil testing to determine the location of the seasonal high water table, which we abbreviate as SHWT here in these slides. We also have soil testing requirements for infiltration BMPs, among other things, and soil testing requirements for construction and post-construction. And lastly, we'll mention what information should be submitted in a soil testing report for your review. So now also covered in Chapter 12 is information pertaining to testing for the input parameters in a groundwater mounding analysis. That information begins on page 29 of Chapter 12 and is also included in Chapter 13. Peter will cover groundwater mounding in Module 3 next week. So there's a misconception that soil testing is required only when an infiltration BMP is proposed. And actually, soil testing is more than just determining the saturated soil hydraulic conductivity. Okay, soil testing also includes finding the hydrologic soil group, the seasonal high water table, and the soil series present on the site. So the identification of the correct hydrologic soil group is essential to performing accurate calculations for the volume and peak flow rate of runoff, regardless of the BMP being designed. Also, many BMPs require separation between the bottom of the BMP and the seasonal high water table. So for example, in a small scale infiltration basin, the 2-foot separation from the seasonal high water table should be measured from the bottom of the sand layer. For a large scale bioretention system with an underdrain, page 11 in chapter 10.1 for this type of BMP specifies the seasonal high water table must be at least 1 foot below the bottom of the gravel layer, inside which is the underdrain pipe itself, and that sits on at least 3 inches of gravel. So if there's no soil testing report showing the depth of the seasonal high water table, you as the reviewer will not be able to judge if this design criteria has been met. So furthermore, when you're using the groundwater recharge spreadsheet to calculate the annual groundwater recharge and the deficit, one needs to know not only the HSG, but the soil series of the soil. So details on this will also be part of Module 3. Now, lastly, the saturated hydraulic conductivity, which generally speaking is the ability of a saturated soil to transmit water, is used in BMP design and for the input parameters in a groundwater mounding analysis. So we're going to go through and see what the soil testing requirements are for all of the various requirements. So the first topic is the determination of hydrologic soil group. So that's used in the selection of the runoff curve number, or CN, as developed by the Natural Resource Conservation Service, or NRCS. So there's 3 methods used to determine HSG. One is from the Web Soil Survey. The second one is called the default method. And then the last one is the HSG testing procedures from subsection 1C in chapter 12. So before we go through each of these methods, we're going to touch on using the old paper versions of the county soil surveys. So we checked with the NRCS and they indicated that they're no longer updating these old documents. The NRCS further indicated the web soil surveys contain the most up-to-date information. So therefore, we are requesting that paper-based information be verified with the web soil survey. So that means the NRCS web soil survey is the first source to be consulted for the HSG information before using either the second or the third method. And just so you know, the NRCS has soil maps and data for about 95% of the nation's counties. So the NRCS web soil survey is fairly user-friendly and it makes it pretty easy to check the accuracy of the submitted information. Plus, if for some reason this information is omitted from the submittal package, knowing how to get the soil survey allows you as the reviewer to continue checking the other parameters used, say in the stormwater calcs without having to first wait for one to be submitted. So at least you can start on your review letter. All right, so to get started with the web soil survey, so once you're on the website, you click the Start WSS button. After clicking the Start button, you begin with the area of interest, or AOI, that's circled on this screen in the red oval, okay? And then either zoom in to the project location using the icons in the yellow oval, or click on the address by the green arrow and then enter the address. Then use the AOI icons in the turquoise ovals to either draw a rectangle or a polygon around the site. I like to check the accuracy of my polygon against the property survey to make sure I got the entire area. The area information will appear under the AOI Properties pull-down menu on the left of the screen above where it says Quick Navigation. Okay, the next tab you'll click on is the Soil Data Explorer tab, which is one of those yellow or tan tabs at the top, and it's in the blue arrow oval that I added. Okay, so next, all right, you're going to select the brownish tab labeled Soil Properties and Qualities, which is in the light blue oval at the top of the screen, and click on the pull-down menu for the item labeled Soil Qualities and Features, located next to the green arrow right there. And then you're going to scroll down to find the hydrologic soil group, which is that brownish bar next to the turquoisey arrow. So if you look over in the image, all right, the orangey outlines in the soil map there on the right, those are the individual soil mapping units. And those are defined as a collection of areas defined and named the same in terms of their soil components, that is series, or miscellaneous areas, or both. Each map unit differs in some respect from all others in a survey area and is uniquely identified on a soil map. So it's a lot of steps, but by following them, we'll see on the next slide that when you click on the pull-down menu for HSG, that will allow you to select the View Rating button, okay, this one with the black oval, okay? Now, when you click on that, the table listing the hydrologic soil group for the soils within your selected area are listed by soil mapping unit, and this table is the white area on the bottom right of the slide you see. The top row in the table is Fort Mott loamy sand, which has a rating of A and covers the area shown on the right side of the table, which is 27.8 acres. The second row is Galloway loamy sand, and we see a double rating in the table. So for soils with dual HSG ratings, which are A/D, B/D, or C/D, the first letter applies to the drained condition, and the second applies to the undrained condition. The appropriate choice of HSG would depend on whether or not the site's been drained. So further investigation will be necessary, and I'll get to that in a bit. So moving down the table to where I have my little red rectangle, you're going to notice that light greenish gray solid area over there on the right of the rectangle. Okay, there's no ratings there. These rows correspond to the two areas of the map that are shaded in the image with that same grayish green color and inside my red dashed ovals. Okay, a lack of rating often happens in urban areas where the soil might have been disturbed or the area has been filled with construction materials. So, for those instances where there is no HSG rating, the soils in the undetermined HSG and the soil series may be determined by the two other methods that I'll get to in just a bit. And they are the default method and the procedures identified in subsection 1C from chapter 12. So one more thing I would like to note is that if it is known that the site has been filled with construction materials, debris, or other material than the soil shown in the survey map, you may not solely rely on the HSG information shown in the soil survey. You'll have to use the other methods to determine the HSG. Okay, so when the HSG information from the web soil survey is unavailable, we use the default HSGs as one of the two methods remaining. All right, and those are used for runoff computations for pre and post conditions as outlined in this table. So HSGs in urban areas are often unknown, and so we would typically use the default areas in these areas. So in the coastal plain, the pre-developed condition hydrologic soil group to be used is A, but for the post-developed condition, you use HSG D. And when you're outside the coastal plain, use HSG B for the pre-developed condition, and then HSG D for the post-developed conditions. All right, now you've also seen this figure, which is figure 12-2 in the chapter, and that's a good idea for a general idea of where the coastal plain is found. So Anthony earlier today showed us how to view the physiographic provinces of New Jersey on one of the department's web pages. So here is that link again to the Bureau of GIS for their interactive website. So you can now enter a location to find out in which province an address is located. So here's what that map on the website looks like when you're zoomed out. The page is interactive and you can zoom in enough to differentiate between two houses on a street. So here's 401 East State Street next to the green arrow, and we see that the site is in the Piedmont province, okay, which is the medium blue shade. The lighter blue area at the bottom of this screen is the coastal plain. All right, so I think you'll readily appreciate how easy it is nowadays to check whether a project is in the coastal plain. So one other thing I want to mention is that for the groundwater recharge spreadsheet, table 12-2 in the chapter has been updated to show the default soil series for recharge computations. This table is on page 6 of chapter 12, and there's a discussion on page 10 in the updated chapter. And we'll, of course, cover this some more in module 3. All right, now if you don't want to use the default HSG values, soil testing to identify the hydrologic soil group must be used. So the third solid bullet that you see is a quote from Chapter 7 of the NRCS National Engineering Handbook, Part 630, Hydrology, which states that the assignment of HSG is determined by the water transmitting soil layer with the lowest saturated hydraulic conductivity and the depth to any layer that is more or less water impermeable, such as fragipan or dorapan, or depth to a water table if present. The least transmissive layer can be any soil horizon that transmits water at a slower rate relative to the horizons above or below it. So, for example, a layer having a saturated hydraulic conductivity of 1.3 inches per hour is the least transmissive layer in a soil if the layers above and below it have a saturated hydraulic conductivity of 3.3 inches per hour. Okay, so you may use the link shown to view Chapter 7, and we're going to take a look at Table 7-1 from page 12 in that chapter. So this table will relate saturated hydraulic conductivity to hydrologic soil group. All right, so here's Table 7-1 from the NEH. So from this table, HSG is determined by depth to a water impermeable soil layer that has a saturated hydraulic conductivity of 0.0014 inches per hour or less. And we also have the depth to the seasonal high water table and the saturated hydraulic conductivity of the most restrictive soil layer within the depth to a water impermeable layer. So according to Chapter 7 in the NEH, certain wet soils are placed in Group D based solely on the presence of a water table within 24 inches of the surface, even though the saturated hydraulic conductivity may be favorable for water transmission. If these soils can be adequately drained, then they're assigned to a dual hydrologic soil groups, which are A/D, B/D, and C/D, based on their saturated hydraulic conductivity and the water table depth when drained. The first letter applies to the drained condition and the second to the undrained condition. So for the purpose of hydrologic soil group, adequately drained means that the seasonal high water table is kept at least 24 inches below the surface in a soil where it would be higher in a natural state. The HSG designation is in the right-hand column of this table. If the depth is less than 20 inches, the soil is classified as D per the top row in the table. All right, where the depth to the water impermeable layer is 20 to 40 inches, okay, we would look in the table in the area of the red oval. Then, if the depth to the high water table is less than 24, we look, 24 inches, we would look at the rows to the right of the orange oval. So this is where we find the appropriate saturated hydraulic conductivity range for the least transmissive layer within the corresponding depth range for the site conditions. So continuing on with our testing procedures, the presence and depth of the restrictions must be included in the soil logs for each soil profile pit and boring. So on the left is a soil sample log showing the depth to the restrictive layer, and the seasonal high water table is shown with the blue line. So now on the right is a shallow soil pit with a face that's been cleaned and prepped for describing the soil profile. So just so you know, this is from Alaska, and this was dug to the depth of the permafrost, which here was only 15 inches. Okay, moving on, we're going to look at the required number of soil profile pits and soil borings that are required for soil testing that is performed to determine hydrologic soil group. So for each soil mapping unit less than a half acre, we need 1 pit and 1 boring. For each soil mapping unit measuring between 0.5 and 2 acres, 1 pit and 4 borings are required. And for each soil mapping unit greater than 2 acres, 1 pit plus 1 pit per each additional 2 acres, and 4 borings plus 2 more borings per each additional 2 acres are required. So the placement of soil profile pits and soil borings is also an important part of the requirement. Soil profile pits and borings should be completed equidistant apart within the boundaries of the mapping unit to provide adequate characterization. So we're going to look at two examples. One is the pink area. That one measures 2 acres in size, and we see 1 soil profile pit and 4 borings. So this configuration meets the placement criteria. For the 6-acre area on the right that's shown in green, we see 3 pits and 8 borings. That's 1 soil profile pit and 4 borings for the first 2 acres on the left, and then 1 soil profile pit and 2 borings for each additional 2 acres, the middle part of the green and the right-hand part of the green. And doing this also meets the placement requirement. Okay, now there's also a depth requirement in the determination of hydrologic soil group. So in the earlier version of this chapter, back when it was published as Appendix E, a depth of 6 feet was required. But now Chapter 12 requires at least 40 inches. Okay, so the presence and depths of soil classification must be included in the soil logs. Okay, so this slide brings us to the end of the soil testing requirements for determining hydrologic soil group. Okay, and there's also an updated workbook for soil testing that you can download from our website. Please make sure you check the date of the update in the bottom right corner of the web page. You should at least see March of 2024. But if you still see tan or orange filled cells, that's the older version of the workbook. Make sure you're looking at the green and the yellow. Okay, this is also included as figure 12-3 in the updated chapter. In the top part, you enter the size of each mapping unit, and the spreadsheet calculates the number of soil profile pits and also the number of soil borings required. The results are displayed in the columns with the yellow fill. Now, the lower part of the worksheet can be used to calculate the depth of a soil profile pit or boring. So based on the information entered, in the event the soil, seasonal high water table is within 24 inches, a message will be displayed indicating that there are HSG-D soils. Okay, so that's pretty much everything I have on HSG testing. So next, we're going to look at the requirements for soil testing to determine the location of the seasonal high water table, and this is found in Chapter 12 in subsection 1D. Okay, so of course, if you see the abbreviation SHWT, that's short for seasonal high water table, but I figure you know that. All right, so pursuant to table 5-1 in the rules, the stormwater management rules, this testing is not applicable to BMPs such as blue and green roofs, as they're constructed as above grade BMPs, plus the others where no separation is listed in this table. Okay, but do note that testing to determine the location of the seasonal high water table is required for those BMPs with under drains, grass swales, and as can be expected, BMPs designed to infiltrate. Okay, so this section of the chapter never stated that under drain BMPs were excluded. So that's why we're clarifying this issue. All right, so let's look at the open bullets. All right, for BMPs designed to infiltrate, we're going to follow the guidance for determining saturated hydraulic conductivity and test at least 2 areas within the footprint, meaning the bottom area of the BMP where infiltration will occur. And for your non-infiltration BMPs, you're going to test within the area to be occupied by the BMP, and the number of tests that are required still follow the requirements for the number of tests required for an infiltration BMP. Okay, so what we're going to, I want to point out is that subsection 2B in Chapter 12 covers the soil testing for non-infiltration BMPs with a required separation from the seasonal high water table. And we'll cover the testing for infiltration BMPs in a couple minutes. All right, so if you're getting inconsistent results in your tests or see such inconsistencies when you're reviewing the soil testing data, then either perform or require more testing be performed, whichever is the case. Now, I've prepared a graphic to illustrate when certain testing and resource data may be used to determine the seasonal high water table. All right, so timing is everything when testing to determine the location of the seasonal high water table. And this slide should clarify some misunderstanding about when to perform soil testing for this purpose. So again, you'll want to look at subsection 1D in the chapter, which has been updated to provide additional clarification. So when you set out to determine the location of the seasonal high water table, there's a sharp divide in how you determine where it's located. And this is based on your observations. That is, the features you see depending on the time of year the exploration is made. Okay, so the next few slides will fill in the details on this graphic. All right, and you'll also see this in page 11 in the chapter. So let's start with the simple case, meaning what applies when the answer to the question of whether modeling observed is yes. All right, so at any season of the year where modeling showing redoxamorphic features is observed, the seasonal high water table shall be taken at the highest level at which the redoxamorphic features are observed, except when the water table is observed at a level higher than the level of the redoxamorphic depletions or concentrations. So for details on determining whether saturated soils are present, there's a guidance document you can look at, and it's prepared by the NRCS. It's called Field Indicators of Hydric Soils in the United States. Okay, so now when modeling showing redoxamorphic features is not observed, the seasonal high water table shall be determined as follows, where A corresponds to the yellow shaded area on the left and B to the arrow with the red bell. Okay, so during the months of January through April inclusive, okay, water levels may be measured directly within soil profile pits or borings. Of course, whenever the department determines that there's been a significant departure from normal climatic conditions, the department may, with due notice to the administrative authority, either lengthen or shorten the period allowed for direct measurement during any given year. Now, in low-lying coastal areas where the groundwater levels fluctuate with the tides, measurement shall be taken at the time of highest groundwater elevation in response to tidal fluctuation. But you know what? There's been no such change in the time frame so far for direct observation. All right, now, during other times of the year, the depth to the seasonal high water table is obtained from the NRCS Web Soil Survey, provided that the soil series present at the site is identified based upon comparison of the soil profile morphology observed within a soil profile pit and the soil profile description provided for the soil series in question within the NRCS Web Soil Survey. So in cases where the seasonal high water table is shown as a range of elevations in the Web Soil Survey, the highest elevation of that range is used as the seasonal high water table. Okay, so this is the complete graphic for your use. So if you're performing your exploration in August and a feature such as modeling is observed, that's where the seasonal high water table shall be marked as located unless the water table is actually higher than, than that. However, did I say August? I think that's supposed to be April. All right. However, for the testing done outside of January through April, if you don't see modeling, yeah, all right, I said it right, it's August. All right, so if it's outside of January through April, if you don't see modeling, you follow the text, all right, in 7:8-5.8.2.b, that's on, it's on this slide, okay? So sorry if I wasn't clear on that, but this should have everything that you need. All right, and for those of you who like text over my graphics, go to tables 12.5 and 12.6 for the guidance on seasonal high water table determination, and that's dependent upon the observations made and the time of the year. So table 12-5 corresponds to item 1 within the citation, okay, and is found on page 12, page 12 of chapter 12, okay? And table 12.6 corresponds to the items 2 under the citation. Okay. All right. So as I said earlier, the department has created some template worksheets that can be used for recording soil testing findings. The third worksheet in that workbook may be helpful for recording observations. So you see here some screenshots from chapter 12. If you go to page 26, figure 12-8 depicts the top part of the Excel spreadsheet created to serve as a template for the soil profile report. All right, there's a column for recording the soil morphological observations and one for the other notes, okay? A good soil log is going to include hue, value, and chroma observed to aid in the determination if redoxomorphic features are present. So moving on, next are the soil testing requirements for BMPs designed to infiltrate. All right, so those soil testing requirements are found in section 2 of chapter 12. So first of all, by infiltration BMPs, we mean a BMP that infiltrates runoff into the subsoils, including such BMPs as can be expected infiltration basins, along with sand filters, bioretention basins, and pervious paving systems designed without underdrains. Testing for BMPs with underdrains was discussed back on slide 16 or so. All right, so let's first look at the number of soil profile pits and soil boring requirements for any infiltration BMP, and that's in subsection 2A of chapter 12. So knowing where the seasonal high water table is located is essential. A minimum of 2 soil profile pits must be excavated within the infiltration area of any proposed infiltration BMP to determine the elevation of the seasonal high water table and to test the hydraulic conductivity of the most restrictive horizon between the basin bottom and the seasonal high water table. Placement of the test pits must be sufficient to provide adequate characterization of the infiltration area. And for BMP infiltration areas larger than 10,000 square feet, a minimum of 1 additional soil profile pit must be conducted for each additional area of 10,000 square feet. At least 1 test to establish the soil hydraulic conductivity must be conducted for each soil profile pit. Okay, so when reviewing the plan, in order to verify the locations and numbers of the soil profile pits, you need to see a site plan depicting the locations of the soil profile pits to show that they are within the infiltration area of the proposed BMP. Now, there is substitution and proximity information found on page 17 of chapter 12. A soil profile pit may be substituted by soil borings only when the conditions stated in the subsection entitled Soil Boring and Profile Pit Locations and Allowable Substitutions, which starts on page 7 of chapter 12, and when those conditions are fully met. The final location of a proposed BMP can differ from the location of a soil exploration. So as long as this proposed BMP is within the same mapping unit, a new soil exploration is not required under 2 important circumstances. So if the soil explorations that have been performed are still within the infiltration area of the BMP at its new location, or if the location of the BMP is within 25 feet in any direction of all of the original soil exploration locations. All right, now also item 7 in subsection 2A includes information on when additional soil profile pits may be required. This is also found on page 18 of chapter 12, and is below it is a table of examples illustrating the number of and type of soil explorations required for various types and sizes of BMPs. So since I've mentioned examples, let's do one. All right, so this is just one, and it's for an infiltration BMP with a bottom area measuring 100 feet by 250 feet, giving us 25,000 square feet. So for this infiltration basin, we need 2 soil profile pits for the first 10,000 square feet, which, since the basin is 100 feet wide, translates to 100 feet of the length as marked here, and then 1 for the additional 10,000 square feet in the middle of the page, and then 1 more for that extra 5,000 square feet on the right end. Okay, so the next few slides are going to look at the number and locations of tests for special types of infiltration BMPs. We'll look at the requirements for small scale and then linear BMPs. And after that, we'll go on to the other tests we need to perform for all infiltration BMPs. All right, so soil testing for small scale infiltration BMPs. So when we have 1 or more infiltration BMPs like this or dry wells, we need 1 soil profile pit for each soil mapping unit where the multiple BMPs are located, plus for our BMPs with an infiltration area less than or equal to 500 square feet, we need 1 soil boring at each BMP. For each BMP with an infiltration area greater than 500 square feet, we need 2 soil borings at each BMP. And for small scale GI BMPs that are arranged linearly, we're going to need 1 soil boring at each BMP and 1 soil profile pit for every 2,000 feet. So this information is written out on pages 15 and 16 in chapter 12 under subsection 2A. All right, so let's move on to the linear infiltration BMPs. All right, so to be a linear infiltration BMP, all 3 of the bulleted criteria must be met, and you'll find this again in chapter 12 on page 15. So a minimum of 1 soil profile pit must be conducted within each soil mapping unit. And in each soil mapping unit, the soil profile pit must be conducted within the first 500 linear feet of the BMP. And when the linear BMP exceeds 500 feet, 1 soil boring must be conducted at every 500-foot interval, and 1 additional soil profile pit must be conducted for every 2,000 feet when you're measured linearly. All soil explorations must be equidistant to adequately characterize the infiltration area. All right, so let's do some examples for some linear infiltration BMPs, and we have 2 sites. The first site is shown at the top of the slide, and it has 2 soil mapping units. So we must include 1 pit for a linear BMP 500 feet in length, shown in the yellow shaded soil mapping unit. And then we need 1 pit for the first 500 linear feet of the soil mapping unit that's shaded in green, with 1 boring for each additional 500 linear foot portion. All right, as long as 2 pits and 3 borings are performed, this example would meet the requirement. For a second example site, there's a linear infiltration BMP with a total length of 2,500 feet, all within 1 soil mapping unit. What's needed is the required pit for the first 500 linear feet, followed by 1 boring for each additional 500-foot increment, and 1 more pit for the additional 2,000 linear feet after the first 500 feet covered by the initial pit. So these are examples that appear as figure 12-4 in chapter 12 of the BMP manual. All right, so let's continue on with the other soil tests needed for infiltration BMPs, and those are the tests to determine soil hydraulic conductivity, depending on whether or not soil replacement is proposed. So for the scenario in which no soil replacement is proposed, after determining the numbers and locations of the soil profile pit for infiltration BMPs, you have to decide the depth of the soil profile pit. Then there's the question of which soil layer to select for performing the test for soil hydraulic conductivity. Well, soil hydraulic conductivity testing must be conducted on the most hydraulically restrictive horizon or substratum above the seasonal high water table or non-fractured bedrock, but located below the lowest elevation of a BMP and above whichever of the following depths is greater. So 8 feet below the lowest elevation of the BMP, or to a depth equal to twice the maximum potential water depth in the BMP measured from the lowest elevation of the BMP. So from our audits, the depth to which the exploration extends to locate the most hydraulically restrictive layer is quite often inadequate. That's going to really affect the performance of the BMP designed to infiltrate. Now, if soil replacement is proposed beyond the required layers in the BMP, the depth is measured from the elevation of the bottom of that required sand or soil layer, okay? So this requirement means first, the excavation of a soil profile pit must reach to the required depth, and second, the hydraulic conductivity must be tested on the most hydraulically restrictive soil layer below the soil replacement or the lowest point of the basin, but above the required soil profile depth. All right, so note that the depth requirement of whichever is greater, 8 feet or twice the maximum water depth, is measured from the lowest point of the basin bottom or from the bottom of the soil replacement, whichever is deeper into the earth. Very often, we've seen the soil hydraulic conductivity test is performed at the top of the soils to be replaced, but not included in the depth of the replacement. And that is the wrong place to do this. All right, so up next is a discussion of what test methods are acceptable for this type of soil testing. All right, and this information is in subsection 3 of chapter 12. Soil hydraulic conductivity can be determined using a tube permeameter test, a percolation test, a single ring infiltration test, a basin flooding test, or a modified basin flooding test. You're going to need to read the specific conditions published in chapter 12 under which these tests can be used. Additional methods of establishing the soil hydraulic conductivity, such as ASTM D3385, the double ring infiltrometer, and USBR 7300-89, well permeameter method, or other soil hydraulic conductivity tests that utilize in situ conditions and are accompanied by a recognized public source reference can be used, such as the Guelph permeameter or the Philip Dunn permeameter, which are available at the Soil Science Society of America book series 5, Methods of Soil Analysis, Part 1, Physical and Mineralogical Methods by Clute, which dates back to 1986. So too often in our audits, we've seen that disturbed samples are used for lab testing. So in your review, make sure undisturbed soil sampling is performed for soil boring explorations when used in any lab-based test. All right, additionally, when performing a soil boring during the soil exploration, the soil borings must be performed and reported in accordance with ASTM D1452, Practice for Soil Investigation and Sampling Auger Borings, and also ASTM D1586, test method for penetration test and split barrel sampling of soils. Sampling must be continuous for the entire depth of the soil boring to fully characterize the soil profile. All right, so since the actual saturated hydraulic conductivity rate may vary from soil testing results and may decrease over time, a factor of safety of 2 must be applied to the slowest tested saturated hydraulic conductivity rate to determine the design saturated hydraulic conductivity rate, which is what is then used to compute a BMP's drain time for the maximum design volume. The exfiltration rate for a BMP allowed to use exfiltration in the routing calculation, or the recharge rate in the groundwater mounding analysis. So one thing to note is that where any tested saturated hydraulic conductivity rate is 20 inches per hour or more, the maximum design saturated hydraulic conductivity rate that can be used in your calculations is 10 inches per hour. All right, the test procedures and conversion equations for the tests shown here are available in Chapter 12 of the BMP manual, and there are even worksheets for some of these. Okay, so we're going to go to section A1 for the percolation test, A2 for tube permeameter, A3 for basin flooding, A4 for modified basin flooding, and A5 for the single ring infiltration test. Now, the cased borehole infiltration test was suspended pending further assessment. The ASTM standard for this test indicated it's not suitable for cohesionless soils. So upon closer review, the soils for which the test would be appropriate would have saturated hydraulic conductivity ratings below the minimum for an infiltration BMP. So as a result, the cased borehole infiltration test has been removed from Chapter 12. For the double ring infiltrometer, well permeameter, or other permitted testing methods, you may obtain them from the American Society for Testing and Materials or the organization that is publishing the test method. So for the PERC test, you're going to follow the procedures described in Chapter 12, and the field measured hydraulic conductivity value shall be calculated using this simplified equation, and that, of course, is in the chapter. So take note that although the test step B in the test procedure for the PERC test requires one to fill the water to a depth of 7 inches, start the time of recording when the water level drops down to 6 inches, and then stop when the water in the hole has emptied. The second worksheet in the Excel workbook may be helpful for your hydraulic conductivity testing. So on the left is the top and middle portion, and that's for the number of profile pits and borings required depending on the type and the size of the BMP. Of course, the lower part of the workbook is on the right, and that's for the depth of the testing. So take note that the title has changed as well as the fill colors, which correspond to the newer version of Chapter 12. All right, so now moving on to what's covered in Section 4 of Chapter 12. So during construction, regular oversight must be provided by the professional engineer to establish that the basin will function as designed. Oversight includes, but is not limited to, the following: a pre-construction meeting with the contractor, confirmation of the proper use of construction equipment, especially to minimize compaction of the infiltration area, ensuring that the earthwork does not occur within the BMP area when the soil moisture content is above the lower plastic limit, and that the specifications of any replacement soils are met. Also, ensuring that proper precautions are taken to prevent sediment entering the infiltration area during construction, or, where unavoidable, if the basin is used as a sedimentation basin, excavation for the sedimentation basin is at least 2 feet above the final design elevation of the basin bottom. Okay, so post-construction soil hydraulic conductivity tests must be conducted to ensure that the installed BMP functions as designed. This is part of the design criteria in many subchapters of the BMP manual. So such testing must be carefully undertaken when all BMP construction that may affect soil hydraulic conductivity has been completed. So that includes the use of all construction equipment and the placement of all construction material that may affect soil hydraulic conductivity. So in addition, hand tools and manual permeability test procedures must be used to avoid affecting the soil hydraulic conductivity. The required number of tests for post-construction testing are as follows. So the number of the hydraulic conductivity tests must follow the same requirements as those for the pre-construction soil hydraulic conductivity tests. And as for the required test steps, the post-construction hydraulic conductivity test must be conducted at the bottom of the excavation of the BMP before the sand layer or soil bed is placed into the BMP. The permitted test methods for post-construction testing are as follows. So only the single ring infiltration test, the modified basin flooding test, and the double ring infiltration test or a similar test that doesn't require a test hole in the soil layer are allowed. The tested soil hydraulic conductivity from the post-construction hydraulic conductivity test must be equal or greater than the tested soil hydraulic conductivity test of the most restrictive soil layer that was tested in the pre-construction condition. All right. Lastly, all post-construction soil hydraulic conductivity tests must be certified by a licensed professional engineer, submitted to the review agency, and recorded in the as-built documents. All right, so far I've covered the requirements for the soil testing that will provide information on the hydrologic soil group that determine the runoff from the site for the saturated hydraulic conductivity that determines the permeability of the soil underneath the basin, and for the seasonal high water table that determines if the BMP can be drained at all. So therefore, I hope you'll agree the soil testing results are essential to adequate stormwater management design. All right, furthermore, since exfiltration is allowed in the routing calculations for infiltration BMPs, the volume and flow rate of runoff that can actually be infiltrated into the subsoil will affect the sizing of the BMP and the outlet structures. So more than ever, soil testing results that correctly describe the soil characteristics are really important. So here's what's required for submittal with the stormwater management report. Okay. All right. The reviewer should make sure that the following is included. All right. And everything here you need is on this slide. All right. So that's just about everything I have for today. And of course, I covered everything that was found in chapter 12. So why you need soil testing, testing for the various reasons shown here, HSG, the infiltration and non-infiltration BMPs, the seasonal high water table location, and the soil testing requirements for construction and post-construction, as well as what should be included in your soil testing report. So as a reviewer, it's very important that the information submitted for an application be examined, as many of the soil reports we've seen in our audits indicate either incorrect or inaccurate testing took place, or even that incomplete information was provided. Right? Accurate testing is required for a BMP to merit the TSS removal rate that's listed in the table of BMPs that may be used to address the water quality standard. The model SCO includes language that testing must follow Chapter 12. So approval of a project for being compliant with the SCO is incumbent upon correct testing. So as a reviewer, please check each and every part of the soil testing information for accuracy, since that's what's going to influence your BMP design. And you'll see some examples in Module 4 that include these checks. All right, so you can reach out if you have more questions, or you can type them into the chat, or you can email us. All right, now, Chengi, if there are no questions, I'll move on to the next presentation.
Please.
Okay, sorry if I ran over. All right, so thank you, everyone. Our next speaker is going to be Dr. Richard McGee from the New Jersey Corporation for Advanced Technology, and he's going to discuss the NJCAT DEP partnership for the verification and certification of manufactured treatment devices. So good afternoon, Dr. McGee. Let me know when it's okay to move on to the next slide.
Hear me?
Yes, I can. You all set?
Okay. Yeah, I'm all set then. Okay,
All right.
well, thank you. Good afternoon, everybody. Here's what I plan to cover in my brief presentation this afternoon. Brief history of the establishment of NJCAT and our working relationship with DEP. Now, many of you know this, but maybe some new people on the line. The role of MTDs in meeting NJAC 7.8. Our program, our verification program, some examples of verified certified technologies, and then really important for you is the misuse of certifications outside NJDEP, and this is what you got to be careful of, and program status as we're moving forward. Next slide, Lisa. All right. Some background material. The state of New Jersey in the late 1990s had discussions ongoing between then Commissioner Robert Shin, former Governor Jim Florio, and the Stevens Institute of Technology President Hal Ravachey for the need to support the development and promotion of innovative energy and environmental technologies in New Jersey. That led to the fact of the 208th legislature that ran from July 1999 to June 2000 to establish a technology verification program. And it basically was Senate Bill number 1750. And it established a technology verification program administered and implemented by NJDEP and NJCAT and appropriated $75,000 to implement the program. After this initial appropriation, you should know that the program has been sustained 100% by fees from the manufacturers to administer our NJCAT program. Now, the Energy and Environmental Technology Verification Act, which became known as under Public Law 1999, Chapter 400, commonly referred to as the EETV Act, approved and outlined the roles and responsibilities of the state of New Jersey, NJDEP, and NJCAT. And by the way, NJCAT was established in 1998. Next slide. Important to this whole program is a performance partnership agreement. This was adopted in June 6, 2000, and some of the applicable directives relevant to the stormwater program as follows, and I'll skip to major bullet 2, is that NJDEP is required to consult and work with NJCAT to develop performance evaluation and verification procedures, processes, and protocols for the purpose of determining the application and use of certain IEETs, studying, evaluating, and verifying the benefits of these technologies, and identifying beneficial and innovative technologies requiring assistance with the regulatory program. To date, NJCAT has focused predominantly on stormwater MTDs, but has also verified some other remediation technologies early in our partnership. And these involved everything from soil washing to in situ chemical oxidation, heavy metals removal from drinking water, and combined heat and power systems, to name a few. Interesting breaking news, so to speak, in November of 2023, which is roughly 1 year ago, an MOU was signed between DEP and the BPU to enable NJCAT, the DEP, to work with BPU to achieve the state's greenhouse gas emissions reduction goals. The initial focus will be on ground source heat pump HVAC system. That program took a while to get the contract in place, kicked off about a month and a half ago, and we're heavily involved working with DEP to work on this ground source heat pump program. Next slide. In Module 1, the history and federal acts predating the post-construction stormwater management program and MS4 permit requirements were presented. In keeping with the requirements of the federal permit, the MTD program complements the department's MS4 permitting program. Next slide. All right, now let's get to the, that was background. Now let's get to the manufactured treatment devices. Basically, as shown here, manufactured treatment devices, which we refer to as MTDs, are a subset of BMPs. They're proprietary, prefabricated stormwater treatment systems that rely upon a variety of mechanisms to remove pollutants from stormwater runoff. Typically, MTDs utilize settling, filtration, sometimes with organic and inorganic media, vortex separation. Sometimes they involve vegetation components and or other appropriate technology to remove pollutants from stormwater runoff. Next slide. The New Jersey Stormwater Management Rules at NJAC 7.8 require major development projects to remove 80% of the project's TSS runoff on an annual basis. It also requires the use of green infrastructure, we call GIBMPs, that manage stormwater closer to its source by either treating the stormwater runoff through infiltration into the subsoil, very similar to some of the material you've just heard from Lisa, as well as option to treat stormwater runoff through filtration by vegetation or soils. And we're going to hear more about that as we go in later into the presentation. NJAC 7.8 provides approved TSS removal rates for both BMPs and MTDs. And what I want you to point out here is, and it's already been somewhat highlighted so far, is that TSS removal rates found in the rules require that all of the design criteria for a given BMP be followed. That's particularly important when we look at MTDs because there have been some instances where manufacturers want to use or propose an MTD in a configuration which was not verified and certified through testing. And basically, the TSS removal rates for manufactured treatment devices are verified by NJCAT and then certified by NJDEP. So it's important that you understand that we verify performance against test protocols that have been promulgated by DEP, and then they take our verification report, look at it, and if they agree with it, they then go forward and issue a certification letter. And only those technologies, only those MTDs that have been certified can be used in New Jersey to meet the requirements for stormwater treatment for sediment. Next slide. So again, we conduct, in essence, an independent third-party evaluation program to verify the performance claims of IEETs. Proudly, I think we can say that the program has strong national and international recognitions. It's a success story. Currently, we're working with MTD developers in Australia, New Zealand, and Germany, for example. And this is in recognition of the great partnership that we've developed with DEP in this regard. Now, the stormwater MTDs are evaluated against NJDEP test protocols. We have two different test protocols, one for hydrodynamic sedimentations, which only allow for a maximum of 50% TSS removal, and filtration MTDs, which can have an 80%. The first set of test protocols were promulgated in 2013, and they've been updated, as you see here, first of all, in January 2021 or 2022, and then updated with minor tweaks in 2023. The reasons for why a new test protocol was put in place, and it was predominantly for hydrodynamic separators, is that industry learned how to game the system. Stormwater MTDs that are verified and certified are the only MTDs that can be used to satisfy the requirements in New Jersey, and I mentioned that already. Currently, you have a list or people have the ability to select 10, and now that number is 11. When I made these slides up, we have one new 11 hydrodynamic separators, 14 filtration devices, and now 13 green infrastructure. And we'll discuss a little bit more about this, but of the currently 11 hydrodynamic separators, remember I told you it went from 10 to 11, 5 will have sunset dates, which means they will no longer be certified in New Jersey, and as a consequence, they will no longer be able to be used on projects. So you need to stay current to make sure that the technologies that are being proposed are in fact on the current list. The most rapidly growing area appears to be green infrastructure. As they say, we're up to 13 now, and this all really kind of began since the year 2020. Since 2020, we've been adding about 2 GIMTDs per year. Okay, next slide. All right, I just want to now just go through, just to give you a little flavor of the innovation and the types of technologies that are in your toolbox, so to speak, if you're going to use it. Look at an MTD. This is called a debris separating baffle box. It was originally in the system by a company called BioClean. This has since expired because it was tested to the old protocol, but other manufacturers have moved into the scene and have submitted. Hydro International has now called it a dry screen next generation baffle box, which is just basically certified in June of this year. But I just wanted to point this out to you to give you some kind of an idea as to how these things work. We usually have an inlet pipe and an outlet pipe, and I want you to be very, very careful to look at those because you'll notice they're in line, okay? Many manufacturers want to take technologies, I haven't seen this one, and build them into a site plan where they may change that pipe design configuration. Obviously, the verification then no longer is valid because that's not what's tested. But basically, this is really one that separates both trash, that's what the screens are for, we'll see that in the next slide, and the sediment falls into sediment chambers beneath that screened area on the top, and that's where you calculate the fine sediment. So this technology has the ability to do both capturing trash as the other ones does as well, but this is designed specifically for that. But because the time for settling is not very long, its ability to remove suspended sediment is in the stormwater is not as effective as other designs. Next slide, give you a different view. You can see here, this is a plain view. The flow comes in one side, it diverts through a screen, which then moves the trash to the left and the back. Only those particles which are smaller than the screen move on, continues to top, and then as it goes out, sediment settles down below into those sediment chambers, which we showed you on the previous slide, and then out the other side. Okay, so that's one type of design. There's a lot of innovation going on, which is kind of exciting from my viewpoint. Next slide. This is one that's in a manhole, which is very, very common. Again, I want to point out you've got the inlet and outlet pipes in line. Flow comes in. We'll see this in the next slide. It hits a flow splitter. It'll go around either side of the flow splitter, but there's also then a oil floatable skimmer, which is up high enough, which will contain any of the trash or any floatable trash or oil that goes at the other side, sump chamber below. Next slide. You can see now it comes in, it hits that flow splitter. As it goes around either side, it causes a vortex motion, which then increases the residence time and the ability to also separate out particles. It goes down below that dividing wall in there, and which is the oil floatable skimmer, comes up the other side, and then it goes through a perforated plate or up through those two major holes at the other side. This technology is one that's going to sunset in December. And the reason being is that the testing was such that they gamed the system and built up, captured a lot of sediment in the inlet pipe, which does not really test the ability of the unit to, particularly at very, very low flows, because that sediment could easily get washed out later on. So the new protocol does not allow you to do that. Next slide. Filters are big. Filters are they can come in bed filters. They can come in upflow beds, downflow beds. There are some membrane filters. Challenges with filters are very, very simple. They clog and they can require maintenance. And as a consequence, there is a reluctance from many municipalities and whatnot to install filters because they're concerned about maintenance, even though you have a maintenance requirement, but then that puts the onus on somebody, i.e. in this case DEP, to make sure they're being maintained. But here you have an inlet. You have a chamber there where you basically can drop out some sediment. You can see there's a sediment. And then there's a hole that then moves you into the next chamber there. That's the inlet window. And then those filters basically treat the stormwater radially inside out. And then eventually they drain down those filters. That way it's set up and there's an outlet pipe. Now, the interesting thing about filters is that this shows you one case with 2 filters, but this Oldcastle says, for example, in an 8x16 vault, this one happens to be a 2 by roughly 5 foot vault. They could have 27 filter cartridge packages. But if you take a look at it and you think about it, how are these working? Well, part of it, and it turns out a majority of the sediment settles out on the floor because these are of the vault, and only a small percentage actually gets filtered through the filter cartridges. So you don't have to worry about that, but there are very prescribed ratios that you have to maintain for any of your vault systems, in this case here, so that you are the vaults that you're putting in with the larger ones have more area for settling outside the cartridges than the tested unit, so that this test here would be considered to be very conservative since they only tested 2 units, and you would still get the performance. But as I say, there's a reluctance to go to filters, and but sometimes it's your technology of choice. Next slide. This is the first one I'm showing you, which is a GI, green infrastructure. You'll notice in here that this is a curb inlet. Runoff comes in the curb, goes into this vault box. It then filtrates through the media below, and then a filter thing goes outside on the right-hand side. And generally, they support for aesthetic purposes, not necessarily they have to, some type of vegetation, in this case, the case of a tree along the way. So this is one of the GI systems. Next slide. Some have taken this same concept, rather than doing it down to a bed, they've actually developed filters, cartridge filters. Here's one with 2 cartridge filters, where again it comes into a vault, and now it's treating it rather than downflow like the other one. It's treating it radially through the media bed, and then there's a when you reach a certain height, the treated fluid then flows down to that center pipe into an outlet pipe, into first of all, a horizontal under drain manifold, and then to the outlet. And again, it's a filter, it's in a vault system. In this case here, obviously, the inlet outlet do not have to be the same, and not even the same location, because the mechanism is occurring through those cartridges in the center. Next slide. Okay, now this is where the rubber hits the road, so to speak. You got to be very careful that manufacturers or site designers don't misuse the certifications. First of all, not all NJCAT verified technologies are NJDEP certified. And that's a confusion to maybe not in New Jersey, but certainly to many municipalities outside the country. In fact, the number of states that rely on the on our program is enormous, particularly if they're willing to accept laboratory testing. But some states don't, I mentioned, do not want to go to filters. So as a consequence, they say, well, you know, what can we do with a separator? Well, New Jersey has a pretty stringent particle size distribution for the sediment that we have to test against. And other states are saying, well, what about if we use a coarser sediment, one which has what's called a larger D50, D50 being 50% of the sediment is below that particle size, 50% is above. Our D50 in New Jersey is 75 microns. In other states, people are willing to accept 120 microns. Well, obviously, larger particles is easier to settle out, and therefore you can have a larger treatment flow rate than you can other. Of the currently certified technologies, I said 33%. That's when it was 12. We just added a 13th, so it's still probably around 33%. But these are GI, and as I said, they're growing steadily per year. Again, only the HDS MTD configuration that was tested has been certified. And as I've mentioned, because I want to make that point, manufacturers will frequently offer other configurations claiming certification. And the three things to be conscious of is one is inlet outlet configuration that is not 180 degrees apart. I pointed that out to you. Multiple inlet pipes. Some people want to bring in two lines into the same MTD. Remember, all of these have only been tested by one. In the new protocol, by the way, there is an option that you can show that your unit can handle two inlet pipes that might be 90 degrees off of the exit line. And if they can demonstrate that by laboratory testing, then their certification will allow them to do that. No one has come in yet. One company is testing their design. They think that they can meet the requirement, but I haven't seen that data yet. And then many people want to have an inlet grate. By that I mean, rather than bringing the stormwater in through an inlet pipe, they want to bring it in through an inlet grate on the top, which can change the whole hydrodynamics inside. So again, my caution to you is, for reviewers, it's imperative that you check the configuration shown on the plan, that it matches the configuration tested as noted in the NJDP certification letter and illustrated in the NJCAT verification report. Next slide.
Hold on one second. Something weird is going on. I seem to be stuck. Bear with me just one moment.
Okay.
Sorry, I'm stuck. So give me 1 second. Give me one. Yeah, I can't move.
Well, the good news is we're almost at the end.
Yeah, I know. I just wish I could advance my slide, but it's not letting me. I've locked up, so this is not good. All right, so I can't even switch to the actual PowerPoint for you.
Okay, I can advance the slides for Dr. McGee.
Thank you.
Shanghai to the rescue.
Okay.
Yeah,
good job. Okay. Another misuse of certifications can be the fact that you have to know whether these technologies have been tested so they can be for offline installation, which means that only the flow rate that they've been tested at manufactured treatment flow rate can go through the unit, or you can do it for online. And to do for online, you have to show that sediment that has been captured effectively will not be scoured out. And that's the concern if you do online. And if there is part of the protocol is if you can test at 200% of the MTFR, manufactured treatment flow rate, with the sediment at 50% capacity captured in the sump, and you don't exceed 20 milligrams per liter of washout, then you can be online. Other than that, you are offline. Obviously, if you're certified for online, you could obviously be offline because that's more conservative. Almost all filters are offline. Almost all hydrodynamic separators are online. It's just how the industry evolves. Next slide. Okay, so the program continues to evolve, and that's important to know. If you go to our technology verification database on njcat.org, we have an expanded and added explanatory text. We've broken down the stormwater technologies into category called laboratory verified and NJDEP certified. So it's very easy for you to see where they are, and they're broken down in the 3 subcategories: green infrastructure, hydrodynamic separators, and filtration. There's another category of stormwater technologies which are only laboratory verified, and that means that, and it's clearly laid out in the report, they did not test exactly to the NJDEP protocol. They wanted to do, for example, a larger D50, and that's specified out, but they cannot be used in New Jersey. There's a category for public review, which just lets you know that certain technologies are still in. We have a very extensive public review process, so some technologies are out there and they have to go through scrutiny by the public, which really means the other manufacturers. And then there's a list of additional energy and environmental technologies. I already mentioned earlier on that some technologies are sunsetting. I think there's at least 16 that have sunsetted already, and the number is growing. And again, it means that they were tested against that prior testing protocols going back to 2013. They're no longer recognized in New Jersey for use. The manufacturers asked that these reports, since they had gone through a pretty rigorous process, be available to other states if they wanted to. So there are 3 categories in here that are listed under archive. They're archived that you could have access to, but as far as you're concerned, make sure that no one tries to tell you that, well, that's they're in the archive section. That just means you cannot use them in New Jersey. Next slide. And finally, the program moving forward, we're managing the implementation of the new HDS protocol. We've got about 2 years under our belts, almost 3 years. And the key here is that that no longer can they play a game by building internal weirs and backing sediment up in the pipe and taking credit for that when it never got into the manufactured treatment devices. We allowed people 5 years to recover their costs of going through the process, and that's some of the reasons why things are sunsetting at different times. And But anyway, that's what's encouraging to see that this whole process, when now that they've learned that they got up their game, I'm seeing a lot of new technology development coming in. One of which just got certified, and several more which I think will be, which is just improving, I think, the ability of these technologies to meet environmental goals we want to have. There's also now something, the ASTM committee has decided that they're now going to come out with protocols for testing. And the interesting thing here is that the ASTM protocols are mimicking very almost identically the NJDEP laboratory test protocols and new ones in that. So that's a positive thing. And we also have a few technologies that were verified only, because they didn't do the thing. They're also going to sunset by December 2024. And this will complete the transition of technology to new protocol. The new game in town is something called the STEP initiative. It's the Stormwater Testing and Evaluation for Products and Practices. This is a heavily manufactured driven program. I'm a little cautious of it because they only manufacturers who pay dues can vote on what goes on there, and they're basically they don't have yet in place a rigorous evaluation process like we do in the NJDEP program has, where outside anybody can challenge the report, and it's my job to adjudicate those challenges and make sure the verification report is as robust and as correct as it can be. And to me, it's been a great value, because no matter how long I've been doing this, and I've done well over probably 50 that have become certified, there are little things I miss every now and then, and this outside review just makes for a better report and a better evaluation of what the technology can do. And with that, Lisa, I think I'm done, and I guess if there's any questions, I can answer them. If not, you can move on.
Well, thank you very much, Dr. McGee. I actually do not see any questions for you in the chat, but if we receive any emails, we'll get in touch with you. Thank you once again. You did a great job.
Okay, well, thank you, and I've enjoyed the other presentations. You guys do a good job. Okay, thanks a lot.
Okay, Cheng-Yi, I think if you would put up the next slide. There we go. So everyone, it will be time for a quiz. Please stand by while Peter takes control, and we'll try and wrap up as quickly as possible.
All right. Hello, everyone. I will share my screen now. So it is time for quiz number 2. As noted before, it is important to complete the quiz now during the time allotted. Note that you cannot move forward to complete a quiz or complete a quiz at a later time. And we need the quizzes to be completed in order to issue credit for the class. So let's get to the quiz. So just like Tuesday, there are a few ways to get to the quiz. Note that if you access the quiz on the same device that's being used for this meeting, make sure to use a separate tab or browser so you are not removed from the meeting. The link at the top of this slide will take you to a page on our website, which includes the handouts as well as each of the quiz links. You can click the link for quiz 2 found at the bottom of the web page to be taken to the quiz and SurveyMonkey. Another way is using the link at the bottom of the slide, which will also be posted in the chat, to be taken directly to the quiz and SurveyMonkey. And lastly, if you want to take the quiz on your phone, you can scan the QR code on this slide, which is also in the chat, to take you right to the quiz. And just a few other notes on the quiz. You must answer every question before you can advance to the next screen and finally submit. You may only take the quiz once. And we're going to do the quiz a little differently today. We're going to be giving you guys the time to complete the quiz, and then we're actually going to move the quiz review to Module 3 due to time restrictions here, since we're coming in on 4 o'clock. So you may begin the quiz, and we'll review it in Module 3, and we'll let you guys know how long you have to complete the quiz. All right, so feel free to get started. Here's everything in one place, and good luck on the quiz. Thank you.